on screen. Terrific. I have to say, for me, it's a little bit of a challenge today because some of you may know I'm actually in Hungary right now, and I'm on an extremely slow internet connection, but it looks like it actually sort of works. It's a real pleasure to be able to collaborate with Nanomath. And we have here some incredible people who are high school students, teaching assistants with Daily Challenge. I'm really happy to introduce, we have Alon, we have Evan, and we have Shankar. And you'll see all of us as we go through some of these questions together. Now, the way that we do this is a live solve. Live solve means that none of us have actually looked at these questions before, and we're going to try to solve them. Does that sound good? So we'll just go through and take turns. And I guess I'll start through with the first one. And after that, let's just go through in like alphabetical order by first name. That's definitive, I guess. So let me give it a go. All right. Oh, yeah, there's my question already. Calculate the exponent of 5 in the prime factorization of 2021. I do want to say the contest that we're doing is from a group called Nanomath. And so congratulations to all of you for making these interesting problems. Although I should say, I don't know how interesting they are. They're probably interesting. We'll see. I bet they're interesting. They were interesting last year. And for any of you who are watching us on YouTube, what we do is we collaborate with competitions like this, and we have some fun doing the questions and then commenting to each other. So of course, like as I'm talking, if any of my co-hosts want to jump in with an idea, just come on in. But all right, so how do you get the exponent of 5 in the prime factorization of 2021 factorial? Well, how do you make 5s? Well, you can make 5s by the 2021 factorial at some point has 5 inside it, multiplied by 10, multiplied by 15, multiplied by 20, and so on. Multiplied by the last multiple of 5 is 2020. Okay, so now what we need to do is we need to know how many 5s there are altogether. And what you might do at first is might make a mistake. You might say, let's just take 2020 divided by 5. What's that? That's 404, I think. By the way I divide by 5 is I just take the number, lop off a 0 and times 2. So that's how many numbers are in this list here. But that's not satisfying because some of these numbers have more than one 5 in them, such as this 25, which is right here. This 25 has 2 5s inside it. What do I do now? Does anyone know? Again, the way you can interact with this here is you just type a message to chat relay. It'll appear on the screen in about 10 seconds. And we have a moderation queue where we can see everything coming through. Well, the issue is that sometimes these numbers appear more than once. So what you do next is you go and see, well, how many 25s are there? And indeed, Ayan, thank you very much for saying that. The shortcut is just to take the 404 divided by 5 again, because like every 5th one of these, there's an extra. And another way to do it, Yushan, is right. You could divide 2020 by 25, but that takes longer. Let's just divide 404 by 5. So for the second row, what I have here is I'll take the 404 divided by 5, round down. That's what this symbol means. That's 400 divided by 5. Using the same trick, lop off a 0. That's 40 times 2 is 80. Okay? But we're not done yet, because there's also going to be some number over here, which is 125. And the 125 is going to add a third multiple of 5, a third factor of 5. So I need to also add on this. This is actually a standard trick. We actually teach this in our classes. But you take the 80 divided by 5 again. And again, only because this is a live solve, so I can't explain every single step. But 80 divided by 5, that's 16. And you just keep going, all right? And slightly dissatisfying for me to not show all of the steps and why they're true, but we're just short on time. So 16 divided by 5, round down, that's going to give me 3, and there's no more that I round down. Okay, Legendres. Vishnu, I'm not sure if that's what I would call Legendre symbols. There's a, but maybe it is. I'm thinking of Legendre symbols in something called quadratic reciprocity, but I just call them the floor functions. Okay, now is the hardest part. I need to add these numbers together. 404 plus 80 is 484. 16 plus 3 is 19. Adding them together in my head. See, I'm adding them together in my head right now. Here's my head. Anyway, I'm not really. I'm writing it. 4 plus 9 is 13. I'm not adding it in my head. Okay, this is 10. I'm going to guess the answer is 503. Is it? Yay! Okay, I'm done. Let's see. Who's next?
All right. Hi, everyone. I am next, I guess, because my name is Alon, and it is A, so it's the first letter in the alphabet. All right, awesome. So let's see. What is this next question? In equilateral triangle ABC, points D and E lie on BC and AB, respectively, such as such that D equals 5, A equals 12, and AD equals 13. Compute the perimeter of triangle AEC. All right, so we already have this nice equilateral triangle here for us. And what we're going to do here is we're going to first label some points, right? So let's let this be A. And I can already tell that I'm way off. I don't know how that happened. Ooh. Let's just start over here. Okay. A. Let this one be B. And this one up here, BC. Awesome. Okay. So let's see here. So let's see. D lies on point on BC, right? Such that D equals 5, A equals 12, and A equals 13. All right. And then so D seems kind of hard to like approximate here because like 80 equals 13. I don't know. We don't really know the side length of ABC, so it's kind of hard to like know where D is about. So let's try doing E first. So we know that E lies on AB, right? And A equals 12. So I don't know. Let's just try putting E about here, or a little higher than that. All right. But yeah. So that's E. All right. And we know that A equals 12. So yeah. And then yes. So yes, you are correct, Alex. 5, 12, 13 is a right triangle. And we will see soon how that will help us. All right. So D equals 5. And we know that D is on BC, right? So let's just put it right around there. That's probably good. I'm not sure though. We'll see. Okay, so we know that 5, 12, 13 is a right triangle. So we know that ADE is a right angle. Oh no, that's not a right angle at all. That's not even close. In that case, let's try moving some points around because we want things to be like pretty close to the actual diagram, if you know what I mean. So in that case, so because we want like ADE to be a right like triangle, right? So like Po just did there, we want for it to be something along the lines of that, right? And that. So that's approximately how diagrams look like. And that's like really the first step in any geometry problem. Draw an accurate diagram, something that I am pretty bad at usually. So yeah. All right. In that case, this one is E, that one is D. And I'm sorry for my amazing handwriting. All right. So compute the perimeter of ADC. We want to find the perimeter of ADC. So we already know that AD is what, 13, right? You know that this one's 5. We know that that's 12. Right, okay. What else do we know though? Well, we know here, well, okay, I don't know. We know that's an equilateral triangle, so that's kind of nice to know. And because it's an equilateral triangle, we know that angle ABC is 60 degrees, right? Hold on. Remember our 30, 60, 90 triangles? If you have a 30, 60, 90 triangle, which that is definitely not, but okay, then this one is A, that one's 2A, and that one's A root 3, right? And the way you can find that is by sort of like completing the equilateral triangle, right? So you like have the equilateral triangle and you split it in half, and one of them is a 3690 triangle, right? All right, awesome. So we see that we have one of those here, right? We have DBE is a 3690 triangle. And because of that, we have that BE is 5 over root 3, and BD is 10 over root 3. Awesome. Now, wait a minute. Now we know the side length of ABC, right? That's awesome. Okay. And what that is actually would be 12 plus 5 root 3 is the side length, which is really good to know. Okay, awesome. And because it is an equilateral triangle, right? All of the sides are the same. We have the AC is also 12 plus 5 root 3. All right, all right. And the last thing we just need to know is that CD, right, is going to be CB minus BD, right? And so CB or BC or whatever is the side length, right? So because of that, CD would just be 12 minus 5 root 3, right? Because you're like subtracting off BD, right? Okay, so then we get that CD is 12 minus 5 root 3. AC is 12 plus 5 root 3. So if you add those up, you get, oh, wow, that is really nice. That cancels out to 24. Okay, awesome. And then finally, we started adding that last 13, which yes, that is a 13. I'm sorry if it looks like nothing like a 13. In that case, 13 plus 24 would be 37. Is 10 over square root 3? Yes, you're correct. BD is 10 over square root 3, But when you subtract BD from BC, you get that is 12 minus 5 root 3, because 12 plus 5 root 3 minus 10 root 3 is 12 minus 5 root 3, right? So yeah. So the answer is 37, which I'm writing on my head as Po did as well. All right. Is that the answer? We'll see. Let's see if it is. It is.
Yay!
Awesome.
Good.
Yay.
Yay.
All right.
Did anyone have any other ways to do that? That's a really suspiciously nice answer.
It is. I agree. It just cancels out really nicely.
Yeah.
Okay, no problem. Who wants to go next?
All right, it's me. E.
Oh wait,
right
one
after.
quick thing before you go, Evan.
Oh.
Maybe you already saw this, but could you spotlight the video rectangle since you are the host now for as minus sign? You just go and find the one. Yes, awesome. Then it's nice and big for everyone to see. Go for it.
Got it. Great. So we have this problem. Bingo number 2. Suppose that m, n, and k are positive integers such that m times n to the k is 100. Compute the least possible value of m plus n plus k. Well, for this problem, we want to minimize what n is, because like when we're taking something to an exponent, it gets really big really fast. So if we want to get the smallest sum here, it'd be helpful to get the biggest thing we can under the exponent. And our first instinct could be to say maybe it's like 1 times 10 squared, but that's actually probably, I'd guess, not going to be it, even though it's 100 and 10 squared is 100. 1 times 100 would be 100. We're sort of wasting m. Like it's, oh yeah, make m and n negative. That would be fun, but unfortunately they say they're positive integers, so we can't do that. But right, for this one, we're sort of wasting our 1, and we're just adding 1 without making our product any bigger. And that's not very helpful. So maybe we could multiply by 2, and then we only have to increase our sum by 1. And we could make this 10 a lot smaller. Well, then we would write 2 times, oh, well, we can't, 50 isn't a perfect power, so that won't work. Instead, we could try maybe m is 4, because 100 equals 4 times 25. And 25 is 5 squared, which actually, those are nice because 5 and 2, they add to make 7, and that's pretty small. It just is kind of small. So then we could say, now that this doesn't work, maybe 4 times 5 squared, and that's 100, and 4 plus 5 plus 2, then the sum is 11. And let's see, would there be a way to make something smaller than this? I don't think so. Yeah. Oh, I see someone here. Yeah.
I'm gonna bet on you because that 25 is nasty.
Yeah. Otherwise, the only place, if we didn't have a 5 in n, if we have a 5 in n, this is the smallest thing we can get. But if we don't have 5, if n is not divisible by 5, then we have to have a 25 out front, and that's not good. It'll make the sum really huge. And I saw someone here said we could set both equal to 10. Well, I suppose that would work. I mean, you could write 10 times 10 to the 1. But then again, we're wasting this exponent here. We want to take advantage of it to get the smallest m plus k. We'll still multiply to 100. So I'm going to guess that 11 is our answer. Because, oh, yeah, k should be at most 2 because 100 doesn't have any perfect cubes. That's right. And it turns out it is 11. Yay!
Yay!
Okay, so I guess I would be next. So let's solve this problem. Okay, here we go. My face cam is not showing up. That is okay. I have more space. So here's the problem. The sequence 2 to the 4, 2 to the 8, all the way up to 2 to the 13.5 is geometric. So that means it keeps multiplying by a ratio each time. Okay, and you just want to find the sum of all the exponents. That's pretty cool. So I don't know. We don't know what the ratio is. So let's just set it as a variable r. So we know that 2 to the 4 times 2 to the r is equal to 2 to the a from our first two terms. That means that 4 plus r is equal to a. Oh, wow, that's pretty cool. So that means that we know that a, or that means that we know that, yeah, a is equal to r plus 4. It's pretty useful. Then we can, let's see what happens if we use that thinking again with the first term, 2 to the 4, times if we go 2 steps forward now to 2 to the 2r, because we want r, and then r again is equal to 2 to the e. Oh, Alex, you said that a, b, c, and d is an arithmetic progression since they are exponents of the same base. That's correct. We keep adding r each time. So yeah, that means that we have 4 plus 2r is equal to b. And the same logic applies to all of our other ones where we have 4 plus 3r is c, and so on. So can anyone tell me what the last term in the sequence is in terms of r? Because then we can solve for r. The last term, yep, I see that 4 plus 5r is equal to 13.5. And that would be correct because 1 is A, 2 is B, 3 is C, 4 is D, and then 5 is 13.5. So 4 plus 5r is equal to 13.5. Then this is pretty easy to solve because we get 5r is equal to 9.5 and r is equal to 1.9. 1.9, there we go. Okay, so now that we have r is 1.9, we can pretty easily solve for what a, b, c, and d sum to because it's just an arithmetic sequence. So a is 4 plus r, b is 4 plus 2r, and so we have, here, let me clear the screen so we have some more space. So we have 4 plus r plus 4 plus 2r plus 4 plus 3r plus 4 plus 4r. Oh gosh, I wrote over the question, but this actually sums to 20 plus 10r. And we know that r was 1.9. That means we have 20 plus 19, which is 39. So I'm going to say that the answer is 39. Let me check. Okay. Oh, it was 35. Did I do something wrong?
Yeah, I think, I mean, I have a different way of doing it, so I got a different answer. But
Oh no.
I'm
Okay.
wondering if it's because of the 4 plus how many r's equals to 13.5. It's 4 plus 5r is 13.5. So I think it's just the division was wrong, maybe. Wait, maybe I'm wrong. 1, 2, 3, 4, 5.
Okay.
4 plus 5r's is 13.5.
Oh yeah.
Wait, that looks okay. Ah, there you go. Anastasia saved us. There you go. Thank you, Anastasia.
Oh no, it is 16 plus 19.
Yes.
That is
Good.
correct. Good job. Yeah. Sorry, guys. Okay.
No worries. That's how this all is. That's why it's in live solve. But I wanted to say there's actually another way to do this. Does anyone see another way to do this that doesn't involve? I saw Evan just nod.
Oh. Sure. Yeah. Well, since they're all in arithmetic sequence, then if you look at them on the number line, then it'll be 4, A, B, C, D, and those numbers are tiny. Okay, 13.5. And then since they're all equally spaced, 4 plus 13.5 is going to be the same sum as, or it's going to sum to twice the middle term, or basically that all of these are, wait a second, 1 gap, 2 gaps. Yeah,
You're good.
yeah, they're going to add the average of all of these numbers is going to be right here, since they're evenly spaced. So that means that since B and C, their average is also this number here because they're evenly spaced around whatever this magic middle number is, the red one. And also A and D are evenly spaced around it. Then B plus C is going to be the same sum as 4 plus 13.5, because it's like we have our average plus a little bit is C and our average minus a little bit is B. And then our average plus a little bit more is D, and our average minus that same little bit more is A, and so forth. So then B plus C is 17.5, which is the same as A plus D, and then their sum is 35. Wait, what? Oh, wait,
Yeah, that's right.
Yeah, 35. Okay.
Yay! So that worked. But I mean, there are many ways to do every question. So it's not bad that we had lots of different things. And oh, Alex Lee also had something he threw in here. So that's good. Have we gone all the way around?
Oh yeah, I think it is now my turn. All right.
Or
Right,
maybe
yeah.
I should
Oh,
jump
maybe
back
you want to
to
go?
me.
Okay.
Yeah.
Sure.
So actually, honestly, I'm also just, as you can tell, I'm practicing here because this is the first time I'm using a setup that looks as cool as you guys's. But I also have to use this tomorrow night because we're doing something for math counts. There's a math counts state competition, and we're doing the official live solve for that tomorrow night. So if you like what you're seeing here, come back tomorrow. But this also means that I need to know how the whole system works. So here we go. What's next? Oh boy. Suppose x plus y plus z equals 0. And x squared plus y squared plus z squared equals 2. Compute the value of xy plus yz plus xz. Ooh, this kind of question. Well, clearly what you do is you try to solve for x, y, and z. No, that won't work for multiple reasons. One reason is because there are only 2 equations and 3 unknowns, so you're dead. So whenever you see that, that's actually a big hint that you should just do stuff to the equations, like multiply them, add them, subtract them. So I'm like, I see squares. So I should just like square both sides of the original equation, right? So the original equation was x plus y plus z equals 0. So like squared equals 0. And as you know, x plus y plus z whole thing squared, that's just x squared plus y squared plus z squared, isn't it? No, it's not. That's where you get all these funny terms, and that's the entire point. So this is x squared plus y squared plus z squared. Anyone want to type into the chat of what else you get? Maybe you can type it and it'll get there roughly as I write it. But it's like x squared, y squared, z squared plus some stuff. And how much stuff? Did I key out green? No, I think I'm good. You can still see green. Okay, good. And thanks, people have written something down. It's 2 times xy plus yz plus xz. Hooray, that's what I want. So now let's just go and look at what I've got. So I've got here a 2. Oh, so if I want 2 plus 2 times something equals 0, then this something here, I think that's minus 1. I'm going to guess the answer is minus 1. Yay! Okay, I got the easiest question. All right, on to you guys.
All right. Turns out that I am getting all of the geometry problems, which is a lot of fun.
Oh no.
Okay. No, it's not very fun for me. I'm not very good at geometry. But let's try this out. Okay, so this seems to be one of those questions that has like you always feel like, okay, is there some like just genius solution that involves moving things around? I hope there is, because I don't want to do a lot of calculation. Okay, so let's see here. If we like sort of take this crescent shape at like the left, let me take a, no, that's way off. Okay. This crescent shape over here, like this sort of shape. And if we were to like move it over here, I think we would get something like hold on. Like we would get like this approximately. Is that right? No, hold on. It's straighter than that. That's wrong. Something like that. Yeah, but like more correct. Okay. So in that case, we also can move the extra shape over here, like the one that's like next to it. And then we get this really nice shape, right? And let me just clear this, because now what we get here is that this whole thing is kind of full, right? So this whole shape is filled up. Is that right? Yeah, I think that's correct. Okay, right. But moreover, hold on a second. Wait. We can do better than that. I think even we can even like move this top shape over here and like reflect it across over here, right? So now what we literally just did here is this really cool thing where we essentially just moved around the shapes to fit a fourth of it. So the answer is just a fourth of the square, right? So the answer would just be 1/4. All right. And my stylus is no longer working for some reason, but yeah, it is 1/4, which means that the answer should be 5. And I hope it
Yay!
is.
Wow,
Is it?
that was
Oh,
an
it is.
amazing
Yay.
solution.
It is. All right, I can't believe I came up with that. That's pretty cool. All right. I think Evan's next, right? Yeah.
Yeah. I just want to say I really like that solution. It was very clever. And now we have this one, bingo 5. Let d of n be the number of divisors of n. Compute d of 10 to the 12 times 11 to the 13. Well, computing the number of divisors of n, well, we can start by writing here 10 to the 12 by 11 to the 13 as its prime factorization. So d of 10 to the 12 by 11 to the 13 equals d of 2 to the 12 by 5 to the 12, because 10 is 2 times 5, but 11 is prime, so it's just 11 to the 13. Now, if we want to see how many divisors this number here has, well, we can use, it's kind of a formula, but also show where it comes from really quickly. So any divisor, it can have a power of 2 ranging from 2 to the 0 to 2 to the 12. So actually, we could just say any divisor of this number can be written as 2 to the a, 5 to the b, 11 to the c. And a can range from 0 to 12. So there are 13 options for a. B can range from 0 to 12, and C can range from 0 to 13. So our total number of divisors is, by the multiplication principle, just multiplying these together, or 13 by 13 by 14. But we're not done yet because it wanted d of divisor of all of this. So then we have to take d of, I'll move this over to the side. Great. And now we want to take d of 13 times 13 times 14. And we can do the exact same thing, prime factorize it, and then use our trick for finding the number of divisors. So this is d of 2 times 7 times 13 squared. And then 2 to the 0 or 2 to the 1. So there are two options. We can also have in any of our divisors 7 to the 0 or 7 to the 1 for 2 more options. And then 13 to the 0, 1 or 2, or 2 plus 1 or 3 options. And that gives us a total of 12 divisors of the number of divisors of 10 to the 12 times 11 to the 13. Let's see, is this correct? Yes, it is. Yay.
Okay, well, I think it's my turn to go. So yeah, I'll do this problem. It doesn't look that bad right now. It's about anagrams. Okay, so a number is an anagram of 2021 if it has exactly the same digits as 2021, possibly in a different order. Leading digits or leading zeros are not allowed. Oh, I see. So yeah, we can't have like 0, 2, 2, 1. Compute the sum of all anagrams of 2021. Interesting. Okay, so let's just like write out some anagrams. So we have 2021. Then we have, I don't know. Well, most of them have to start with 2. It's like it either starts with 2 or it starts with 1. So we have 2, 0, 2, 1, 2, 2, 1, 0. So all of these random numbers. So we need to find a quick way of organizing these and then summing them. Well, I think our first intuition would be, 2012 is one of them. I see that Shadow Wolf has said that in the chat. So 2012, yep, that's another anagram. I have all these anagrams, but we need a quick way of organizing them. And what we can realize is that they either start with 2 or they start with 1, right? So how many start with 2? Yes, it would be combinatorics. Okay, so how many start with 2? We can either, so we have 2 and then some permutation of the other 3 numbers, right? So that would be 6 total that start with 2, because it can't start with 0. Then we're going to see what happens if we start with, so, and then out of these 6, we can just sum them by their digits. So all 6 of them start with 2 in the thousands digit, so that's 12,000. Then in the hundreds, units, and tens digits, it's just always some permutation of 0, 1, and 2, right? So that means, so we have like, it's just all the permutations of 0, 1, 2. So it was like 0, 1, 2, 0, 2, 1. So it's, and it's pretty easy to see that there's going to, out of the 6 of these, each sum would have to be 6, right? Unless I'm not doing something right. Each like total sum in each of the digit columns would be 6. Let me try to be more organized, because so 0, 1, 2, 0, 2, 1, 2, 1, 0, 2, 0, 1, 1, 0, 2, 1, 2, 0. There we go. So yeah, as we can see, each of the sums is 6. So that means we add 666 to our 12,000, right? Yep, so 666. Then we have to do the case. So this is 12,666, that's our number. Then we have a case whenever it starts with 1. So here is a new page, and let's see what happens. So now we have 1 and then some permutation of 2, 0, and 2. But there aren't that many of these. Okay, well, kind of writes over the question, but whatever. So can anyone tell me in the chat how many permutations there are of 2, 0, and 2? 3. Yes, that is perfect. There are 3 permutations, because it just depends on where the 0 goes. So 2, 0, 2, 0, 2, 2, and 2, 2, 0. And so you can see it sums to 4, 4, 4, right? So there's, and then this would sum to 3. So that means the sum of ours, whenever it starts with 1, is 3, 4, 4. So that means whenever we had started with 2, it was 12. Is that okay? Yeah, 12, 6, 6, 6, right? Then whenever it started with 1, it was 3, 4, 4, 4. Those are only cases, so we add them. Hopefully I do not mess up my addition this time. Oh, I messed up my addition. This, or did I? Yes, I did. I knew I messed up my addition. Okay, I can't add, so 0, this is 11, this is 11, this is 6, this is 1. So I think the answer is 16,110. Let me check. So, okay, here we go.
Yay!
Hey, there we go. Okay, yay.
Awesome.
Okay.
I think I'm up next. I also don't see a better way to do that than what you just did.
Yep.
I see my co-hosts are nodding, so that means I think we agree. Okay, so let me go on to the next one. What's next? DC16 lower div number 3. Interesting. I wonder what this means. Compute the number of ways to paint each of the digits of the number 1, 2, 2, 3, 3, 3, red, white, or blue, such that the first 2 digits are painted different colors. At least one of the 2's is red, and at least 2 of the 3's are painted different colors. This is a mouthful. It's going to take me a bit of time to figure this out. So, all right, I've got reds, whites, and blues. The first 2 have to be different colors. At least one of the 2's is red, and at least 2 of the 3's are painted different colors. All right, so the way I see this is that the 1 And the threes are like a different world from the ones and the twos. So I'm just like parsing the question here. And I see that there's some comment about the threes. And that comment about the threes does not involve anything about the ones and twos. So I can just go and figure out how many ways there are to paint the threes and then multiply it by how many ways there are to paint the ones and the twos. If I want to know how to paint the threes, at least two painted different colors just means not all the same color. Okay, so if I want not all the same color, not all the same color, well, there are three colors for each of the threes. So can anyone type into the chat if there are three choices of a color for each of those threes? How many ways would there be to color all the threes if I didn't care, if I don't care about them being not all the same color? What do I do with all these three choices? Yes, that's right. So I see people asking, is it 3C2? Is it 27? It's actually 27. There are three cubed ways. There's going to be a minus sign, don't worry. So let me write this more legibly. I need to have a 3 cubed minus something, right? Because 3 cubed is the number of ways that I can just like color the threes with like three choices for each one. And now how many do I subtract? Anyone want to type into the chat? So I need to subtract the ones which are all of the same color. Thank you very much, Anastasia and Nived as well, minus 3. So that's equal to 24. Okay, but now I need to deal with the ones and the 1, 2, 2 business. So the first two digits are painted different colors, and at least one of the twos is red. All right, so I guess I'm just going to break the other one into two cases. Okay, the other one is the number of Among Us maps -1. That's cute. Okay, so how about this like 1, 2, 2 business? Okay, so I'm going to do case 1. I'm now going to do the 1, 2, 2 stuff. Well, let me just use colors to indicate what I'm doing. So the first two digits are painted different colors, and at least one of the twos is red. That's my green stuff. Okay. And so for the green thing, I'm going to break into two cases. Case 1, which is that the first two is red, and case 2 is that the first two is not red. So first two is red. If the first two is red, I no longer need to care at all about the at least one of the twos is red, because that's already done. And I need to have that there are different colors. So can anyone tell me how many choices there are for the first digit now? The 1, how many choices are there for the color for the 1, given that the first two is red? And I need to have that the first two digits are painted different colors. Anastasia, very quick. That's right. It's 2 ways. So there's 2 ways to color the 1. And then we have to multiply that by, well, the second 2. So for the second 2, how many choices do I have? I already colored the first 2 red. Anastasia, that's right again. 3 ways to color the second 2. So far, this is 2 times 3 is 6, but I need to do case 2 also. Still in the green section. The green section is this one where I have, I'm just dealing with the green text up here. And so now I need to say the first 2 is not red. Oh, by the way, I've got choices here already. How many ways can I choose a color for the first 2 not to be red? Well, just not red, right? So that should be 2 ways. After that, thank you, Aria, for saying that. And boy, actually, no one else can see that. Well, you can't see the comments that people have made, but I can see them 10 seconds before they show up. But the next thing is that we also want to know, okay, how about that color number 1 at the beginning? Oh, yes, the color for the number 1 has to be different from the color for the number 2. So times 2 ways to color the number 1. And then now I'm stuck, right? That's why I see Ray and Zhao, you're right. I've got only one choice for the second 2. It's red, because at least one of the twos has to be red. Times 1 way to color the second 2, which is red. All right, so that's 2 times 2, that's 4. Now I need to take the 6 and the 4, add them together. I get 10. Can anyone tell me what I do to get the answer now? Maybe you were listening. So I now know how many ways there are to do this pinkish purple thing. Anastasia, thank you. I'm going to want to multiply the 2 numbers, the 10 and the 24. I can multiply those in my head, 240. I think that's my idea. Let's see, is that right? Yay, okay, I survived. Alon, it's on to you.
All right, so we are going at another geometry problem. Seems like by the end of this, I'll actually be a little decent at geo. So let's do this. Arpit goes to the store with 5 of his friends and buys a beautiful cylindrical cake with a base radius of 12 centimeters and a height of 6 centimeters. He cuts the entire cake into 6 equally sized sectors, and for each slice, covers all faces except the bottom with a thin layer of icing. Suppose the total surface area of icing on all 6 slices, in square centimeters, is of the form a plus b pi. Compute a plus b. All right. Yeah, another geometry problem. This is going to be so fun. All right, so, okay, so cylindrical cake. So he has this, it's kind of like a circle, right? So, yeah, it's a beautiful circle. Yes, that is a circle, I'm sorry. Okay, so it has a base radius of 12, right? So like, that is 12, right? And so what he does is he cuts it into 6 equally sized slices. So something like that, right? All right. And so what happens actually is that so we just want to find, right, like the total surface area of these slices, but except for the bottom one. Okay, so what we could do is we could just literally find like the surface area of like each slice and then just add it up, right? But let's do it in a smarter way. So what if we only consider like the top part? Okay, and we just like find all of the top faces together. How much would that be? Does anyone know? How much would just the top faces for all of them together be? All right, well, that would just be, yes, exactly. That'd be 144 pi because it's just the top face. It's literally just the top face of the cake, which would be a circle, right? With circle radius 12. So that would be 144 pi. Awesome. Right. Now, okay, let's find all of the like the lateral faces. So all the curved faces actually. Let's do that. What would the curved faces be? So we have that like all the curved faces together. They would be sort of like the lateral face of the cylinder. So what would that be? Well, the circumference is going to be 24 pi, and then the height is 6, right? So exactly 24 pi times 6, and 24 pi 6. Let's do this in my head, just like Professor Loaded. So that's not even close to my head. Okay.
Your ideas are higher than mine.
Oh, okay, that's a good one. All right. Yeah, in my head, that'd be 24 times 6, which I think that should be 144. Yes, thank you. Thank you. I can multiply, I think. All right. So 144 pi for like the top face and the curved faces. All right. Okay. Now the next ones. So all the inner faces. Okay. So we have that there's like 6 slices, right? And each slice has 2 inner faces, right? And so because of that, there's 12 faces total, right? And so how much is each inner face though? Well, each inner face is a rectangle, right? So it would be 12 by 6, because 6 is the height, right? And there's 12 of those. So as I said in the chat, it would be 12 times 12 times 6, which should come out to be 144 times 6. And as usual, I'm writing on the question. All right. 144 times 6, what would that be? Let's test my multiplication skills. 864. Thank you. All right, 864. And so because of that, the total area total surface area would be 864 plus 288 pi, right? And then what we want to do really is just figure out what 864 plus 288 is, which I hope I can figure this out. All right, I'm going to cheat. I'm going to use the chat, and I'm going to say, yeah, it's 1152, because I definitely can add. I hope so. All right. Yay. So the answer should be a 1152, which it is. Yay. All right. Awesome.
I think
Evan's next. Yes, Evan.
And he's got a cake.
Yeah, I just drew a cake because I had some time, and I'm so proud of it that I'm going to leave it up there. It's a wonderful cake. Okay, and now for this question, Square, oh, circles and squares. Actually, that's good. I like it when I see squares around my circles. That tends to be nicer than other shapes. But square ABCD has side length 8, such that each side is also the diameter of a circle. Okay, and the total shaded area is a plus b pi, and we want a plus b. Okay, and just the diagram here. Well, we can just find the area of one of these little leaves, and then we're basically all set. We could also find the area of one half leaf, which would sort of look like this. Yes. And actually, this is a lot easier to find because we could continue the circle, and this circle looks more like an egg with a sort of protrusion, but that's okay. We want to find this area. I'll shade it in. And we have this. And from our original diagram here, does anyone know what this angle here, or this central angle, is going to be? Yeah, it's 90 degrees because here we'll have that line and then that line, and it's a right angle because of square. And yeah, like you guys are saying in the chat, the radius of this circle is 4 because this whole side length here is 8. The radius will be half that, or 4, 4, 4. And so the area of this whole chunk of the circle, all of this stuff, is 4 squared pi over 4, because we're taking 1/4 the area of the circle. And that is 16 pi over 4, or just 4 pi. And then we'll want to subtract out this area here, this red right triangle, because right now we have the area of the red and the yellow combined. We'll subtract out the red, and that's just base height over 2, which is 8. So our yellow half leaf is 4 pi over 8. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8 of these. So our total area will be of our total purple area. Oh, I'll use this blue because it's purple. 8 times 4 pi minus 8, or 32 pi. Oh, it changed to orange. Well, that's okay too. 32 pi minus 64. Yes, like Edison says. And then what did they want? A plus b? Cool. And then that's just 32 minus 64, or, and here, let me scooch down, negative 32. And I've written it myself into a corner, so I sure hope it's correct. And it is! Yay! And I think I'll only take off the stuff that's not a cake.
You gotta keep the cake. That's great.
Okay, well, here is the problem. So compute the number of integers between 1 and 2021. Oh yeah, hi, here I am. Okay, that can be expressed as the difference of squares of 2 distinct integers. So a squared minus b squared is equal to some number x between 1 and 2021. Does anyone have any ideas that they would like to share in the chat? Okay, I see difference of squares. So the difference between 2 consecutive numbers is always equal to the sum. Those are 2 great ideas. So yep, a squared minus b squared is a plus b times a minus b is equal to x. Yes, and Shadow Wolfie said the difference between 2 consecutive squares is always equal to this. Well, we know that any number that can be written as like a plus b times a minus b is automatically good. So, well, as long as the number can be split into 2 factors, and then there's a solution for a plus b times a minus b, then yeah, it works. So I see this is either always odd or a multiple of 4. Do you want to unmute and explain what you mean? All odds work because you can just take 2 consecutive integers and scale up by any square number. So so you can scale up by any square number. So you can scale up 2, 4, 8, 16 to get everything except powers of 2 work. So do you want to unmute and explain what you mean by that, Ray Zhao? Oh, so so if you have 2. Oh, I see what you're saying. So whenever A and B are consecutive, then you can get like so many numbers, like you can get all the odd numbers like that. Oh, that's oh, and so you need to subtract those. O- Okay, so how would you count those? 'Cause you are really good at this problem. Uh, I, I, yeah, yeah, there's definitely a great solution with casework, but I think Professor Lowe has a really cool solution without as much casework. So Professor Lowe, do you want to share that?
Yeah, sure. Okay, no problem. I can take that. Actually, I should say it was inspired by Ray talking, because at first when I was typing into all our chat, which I realized I had forgotten to unmute, so you probably heard this ka-chunk, 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 ka-chunk. That was me. I was telling all of our co-hosts, like, man, this is painful. I'm thinking, I'm glad I didn't get this question. But then as I kept listening to you guys, I was like, oh yeah, that's right. You can get consecutive numbers, right? So let me explain this one instead of being explaining the next one. And then after this, Alon, you can take the next one. So this is just like inspired by what I heard all you guys say, right? So it's like, suppose I want to get a difference of some random odd number of, like, I don't know, what's a random odd number? 23. 23 is as random as you can have. Okay, it's 23. 23 is an odd number. You can break 23 into the sum of two consecutive numbers. You said Shadow Wolf wants me to use 21 instead. 21 doesn't look as random to me for some reason, so I'll just stick with my 23. But actually, 23 is less random because it's prime. Oh, you want 21? Okay, fine, we'll do 21. Okay, not okay, fine. It's like, okay, you want 21? It's 21 now. All right, so we got 21. And now I want to make that into the sum of two consecutive numbers. Every odd number is the sum of two consecutive numbers. That's 10 plus 11. And many people were typing into the chat, when you subtract two consecutive perfect squares, the answer is the sum of those two numbers. You see, 10 plus 11, that's equal to 11 squared minus 10 squared. And that's because of this difference of squares thing that Shankar wrote down, right? Shankar was like a squared minus b squared is a plus b times a minus b. And the a plus b here, wait a second. Yeah, the a plus b here, that's the 11 plus the 10. That's here. And then the a minus b is 1. So, okay. So basically, any odd number that you want, you can actually get as a difference of two squares. And you always want to check the beginning, because sometimes weird stuff happens at the very beginning. Like, can I get 1? If I want a difference of 1, is there a pair of perfect squares that will give me that? Can anyone type into the chat? If I want a difference of 1, 1 is 0 plus 1. Aha, and I see. So thank you very much, Shadow Wolfie. That's going to be 1 squared minus 0 squared. So this is telling me that I can use this kind of a technique. I can get all odd numbers. Okay, well, at that point, then I'm inclined at first to say, I must be done, that must be it. But no, because there are also ways to get differences of squares that aren't odd, right? I can also take differences of squares. And once you think about this, it's like the gaps between differences of squares are actually consecutive odd numbers. That's very useful. That's a very useful fact to know, that if I'm going from like 0 squared to 1 squared to 2 squared to 3 squared to 4 squared and so on, 5 squared. Can anyone tell me what are these gaps between them? The gap between 0 squared and 1 squared, that's a 0 plus 1, which is equal to 1. The gap between 1 squared and 2 squared is 1 plus 2. I see that one of our co-hosts has a fan club. We get to see all the messages that come in, whether they show up on the screen or not. But yeah, that's cool. Okay, so 1 plus 2 is 3. The gap between 2 squared and 3 squared is 2 plus 3, which is 5. And then the difference between 3 squared and 4 squared is 3 plus 4 is 7. They're consecutive odd numbers, right? 1, 3, 5, 7, 9. So at that point, I can also get differences of squares, like the difference between 2 squared and 4 squared. That's going to be the sum of these two numbers. That's going to be 5 plus 7. So at that point, what I need to do is I need to be like, what other numbers could I possibly get by taking like sums of consecutive bunches of these? Because the difference between like the 1 squared and the 5 squared, that's just going to be 3 plus 5 plus 7 plus 9, right? So the next thing is like, oh, gee, I could add 2 of these consecutive odd numbers. And when you add 2 consecutive odd numbers, 1 plus 3, that's 4. Let's look at what these are actually. If I take 1 plus 3, add them together, that's 4. That's the difference between 0 squared and 2 squared. Meanwhile, the difference between 1 squared and 3 squared is 3 plus 5, which is 8. And the difference between 2 squared and 4 squared is 5 plus 7, which is 12. Does anyone see a pattern here? All of these numbers I can also get as the difference of 2 squares. I can get 4, I can get 8, I can get 12, multiple of 4. Thank you very much, Shardu. So I can get actually any multiple of 4 this way. And the reason you know this is because if I've got some random multiple of 4, well, that's going to be double an even number. Okay, I'll go figure out where that even number is, and I'll take the 2 odd numbers right around it, and bingo, those 2 are going to be differences between consecutive squares. And then so that difference is going to be just, that multiple of 4. So using this next technique over here, this gives me all multiples of 4. Get all multiples of 4. And then the only question left is there anything missing? So right now, the things that seem to be missing are things which are what's called 2 mod 4, which is multiples of 2, but not multiples of 4. Could that ever happen? Well, now we've got to think about this difference of squares thing. If I have this a squared minus b squared, which was a minus b times a plus b, can it be even, but not a multiple of 4? Hint, the answer is no. But does anyone know why? Can anyone type into the chat a reason why, if I multiply these two numbers together, it's never going to be even and a multiple of 4? Oh, interesting. So, okay, there's a couple of different solutions that have come in. Ray has said that all squares are either 0 or 1 mod 4. That's one way. But I was actually going to say the same thing here, Shardul and Alan. The difference, like these two have the same parity. It's that a minus b and a plus b are either both even or both odd at the same time. And actually, the reason is because the difference between these two numbers is exactly 2b. Does that make sense? This number to that number is plus 2b. It's plus an even number. So if I look at this number and I look at this number, their difference is 2b, which is even. And so that's why like they're either both even or both odd. So if I have both even or both odd, it's like poof, it has to be that's it. It just has to be that either you get multiple of 4 already or it's odd. Okay. Oh, wow. So the answer I'm going to say right now, we're going to finish up because actually also my co-hosts have pointed out, we are unfortunately over time. So let's see. So I'm going to be like, oh no, this is going to be hard now. How many numbers are not 2 mod 4 is what I need to figure out. I need to subtract that from 2021. Okay. So how many, I'll count how many from 1 to 2021 are 2 mod 4. Well, from 1 to 4, from 5 to 8, all the way up to 2020, that's like a perfect bunch of groups of 4, right? So if I remember correctly, well, not remember, I look at it, it's like there are 505 groups of 4 that will get you to 2020 and the 2021. But in these 505 groups of 4, each of those groups has 1, which is 2 mod 4. Each of them has 1. Each has 1. And so my answer, how many are 2 mod 4, is going to be 505. Okay, so the answer is 505 are 2 mod 4. And I need to subtract that. So I think the answer is going to be, I'll do it in my head, 2021 minus 505. Oh, what do I do? This is too hard. So I'll do it in my head, which is called subtract 500. That's 1500. And then subtract 5. Is that right? I hope so. Let's find out. Yay, it is. And with that, unfortunately, we have to call it a night or a day. It's a night for me in Hungary. But the reason we have to stop is because actually we have other things that we're running. If you liked what you saw here, we actually run all of our middle school online classes in this way, actually taught by incredible people like who were with you here tonight, our high school co-hosts, which obviously already have a fan club among the audience, which is fantastic. And so we have to sign off because we actually have more events that we are working with our teaching assistants to help them learn how to teach even more effectively. And so I have to run off to do that. But thank you very much to the organizers of Nanomath. You guys wrote some very interesting questions. Thank you to my co-hosts for coming on tonight. This was certainly a lot of fun. And wish all of you guys a good day or a good night. Take care. Bye.
Bye.
Evan, you're the guy with the power over the meeting. So you're able to close out that meeting whenever it's time. Thank you, everyone.
Hi, everyone. Thank you for coming.
Thank you.